There was homework due today. And the homework was to take your Hello program and change it from a program that used main and was built with the C runtime to one that was built to just be its own little process without the C runtime in it. And along the way to check the arguments and to become a position independent, dynamically linked executable. All those are good things. And you needed to pay attention to the calling convention when you called something, but since you were writing it from the point of view of the start of the process, you didn't need to worry about anyone calling you, right? We'll talk more about that in just a moment. And the build line down at the bottom was your hint. The build line at the bottom doesn't use GCC, it uses LD. And when you run that build line, it's going to look for underscore start in order to build it. argc at the top of the stack, argv is right below it, or at least argv0 is. argv itself is just a pointer to that location, which happens to be on the stack. I had some hints for you. Again, pay attention to registers. You've always got to do that. That just is the way it is. Let's talk briefly about tools, and the tool we're going to talk about is more Python. Arrays are super useful. They're going to be really useful for what we're going to be doing next. So let's spend just a few minutes talking about how arrays work in Python. Sorry, I'm drinking tea, trying not to cough too much. An array in Python is like an array in any other language. It's just a linear collection of stuff. Now, in most languages, you have to have things all be the same type, but in Python, arrays can be heterogeneous, meaning they can contain lots of different stuff. So up at the top on the right there, we create an array that holds 3 integers and the name Reka. So there you go. And when we look at it, Python reports that it's an array, and you just basically put the things in square brackets and you put commas between them, and that's an array. They're indexed starting at 0, but you can index them with negative numbers, and that indexes them from the right. So if I say x of 0, I get 12, x of -1, I get Reka, which is the last entry in the array. So they're kind of neat in that regard. You can take slices. I think we mentioned array slices last time. Slices are really a useful, helpful thing, not just for throwing away the first command line argument, but also for manipulating big arrays, maybe big arrays of bytes that might come to you from, I don't know, the text section of a program. Could come from anywhere. So x5, again, 0 base, 0, 1, 2, 3, 4, 5. That looks like 32, and that's in fact what Python tells us. This is a fun slice. This is everything. It's just a fancy way of saying I want everything. If you don't specify the start, you get the first one, 0. If you don't specify the end, you get the last thing, which is -1, and you're good. I could slice off the first element. So instead of starting at 0, I start at 1. And sure enough, Carmen's gone, which is sad for Carmen. I can slice off the last thing by specifying -1 over here. And that 22 is now gone from the end. I can do this. So what is this third thing here? When I have 2 colons, I have the start, the end, and a stride. So this is how much I count by. So I run through the whole thing, but I count by 2. So I get every other element. So I would get Carmen, and then 2, and then 0, and then 22, right? 16 plus 6 is 22. And there you go. Here I start at 1 and count by 2. So I get the other elements, the odd ones. If I specify this, right, start at 1 and then end at 1, this emphasizes that I count up to, but not including this last item here, right? That's why this :-1 drops the last thing, because it counts up to, but not including the last index. And so you can see that returns me an empty array. And Python is perfectly fine with me saying, asking for crazy things. It will do a best effort to give me back what it has. So for example, here I say, I want the array from position -8765 up through position 876. Those are clearly insane numbers, but Python happily accepts it and gives me back, in this case, the entire array. So it's pretty tolerant of you doing some crazy stuff, which can hide errors in your program, but can be useful in other regards. There you go. So some quick information on slices and arrays in Python. I posted a little video where I talked about starting programs and starting processes under Linux and so on. And it occurred to me that I should just go ahead and commit some of that information to slides. So here it is. We're going to talk about processes and _start and main and maybe argc and some other stuff. Linux process. How do things get started on Linux? You should know this because this is how they get started under anything, under any Unix-like OS. In fact, this is how they start on Windows. Fork. Fork is a system call. It's number 57. Takes no arguments, and what it does is it builds a new process space. And it does this by explicitly copying the page tables of the parent process. So there's a brand new copy set up actually in DRAM of the page tables. You get your own independent copy of the page tables. In addition, you get your own PID. The new process gets its own process ID, and its parent process ID is the parent process that just tried to fork it. That parent can go away. If it does, then the parent PID gets changed and to point to something else, like init or in some cases a grandparent. Just varies. So you get your own PID, you get your own process space, and you get a copy of the parent process's memory, sort of. Remember, memory is virtual. So what actually happens is it just assigns you a memory space, and it maps in the stuff from the parent's memory space into your memory space. Well, that could be bad, right? If I write to something, I could be writing to memory that the parent is depending on. That could be a problem. And so what happens instead is copy on write, which means as long as I don't need to write anything to it, it's basically zero cost. But if I want to write to memory, then I get my own copy of that page that I'm going to write to, and I write to that page, so it doesn't affect the parent's memory. This can make fork fast. It used to be that fork was very slow because it actually had to duplicate the memory. Now it does it through the magic of virtual memory and page tables. Okay, but you do get a real copy of the actual page table itself. And if you think about this, right, we're doing the magic through the page table. It makes sense for you to get your own real copy of the page table. And that actually enables vulnerabilities like rowhammer. So if you can think back way back, I think at some point we may have mentioned rowhammer. Rowhammer is a vulnerability in systems that use capacitance-based memory like DRAM. And the basic idea is that I can hammer on the rows in memory. I can write to them, really fast. And if I do that enough, changing the bits, I will get a random accidental bit flip in memory. They happen all the time in the DRAM, but it's statistical. And there are processes to correct for it. But if I can do that, I can sort of force a quote unquote random error to be much less random, because I'm right. I mean, if I only have a 1 in 100 chance of something happening, but I do it 50,000 times, it's probably going to happen. Right? So I can get a bit flip. Well, a random bit flip somewhere in memory doesn't help me unless I've set up memory in such a way that a random bit flip likely does help me. And one way to do that is to fill memory with something that I'd like to be able to change, but normally can't. And that thing is the page table. And so if I can cause enough copies of the page table to be built, then I can use a technique like rowhammer to cause a random bit flip in it, which may result in me gaining access to something the page table points to. And since most of memory is full of page tables, it points to other page tables. And now I can manipulate a page table, and that basically gives me control of the machine. Not something you need to worry too much about, just a fun fact about copying the page table. All right. Under the hood, the kernel actually uses something called clone to implement fork. If you're curious about clone, it's the syscall number 56. And there are a couple of variants of it, but you probably don't ever need to worry about it. Fork makes you a new process space. Then you can call exec VE. So after you fork, you get a process space that's a copy of your parents, but you don't want to be like your dad. You want to go out on your own. And so what you immediately do is call exec VE, which is number 59. And it takes 3 arguments. It takes a file name. It takes a char star star, which is argv, and another char star star, which is your environment. And the kernel goes out and reads the file specified by file name if it can be found, right? If it can't, you're going to get a file not found here. And it tries to determine how to execute that file. The argument list and the environment are given as arrays. The underscore user stuff up there, that's really just there as a hint to the kernel that you're pointing to something in user space that you control, and that could be a security threat, so the kernel should be careful how it uses it. You should not trust that information. File has to be executable. When we look at the file, the first two bytes are a hash mark and an exclamation mark, or a pound sign and exclamation mark, whatever you want to call it, a shebang. Then the following text contains an interpreter directive, and you've seen that, right? I mean, you see that in bash scripts, you see that in the Python files we were looking at last time, and that basically just says, here's a file, but I want it to be interpreted by this other program, and I can specify the program that way. Otherwise, the first byte should specify a known magic number, and there actually can be several of those. You can install code under Linux that lets you execute different kinds of files. Like you can go back and actually I think you can still get support for the old a.out format under Linux and install that, but don't do that. So it looks for that, and it tries to see if it's something that it can run. The magic byte sequence for ELF is 7F, and then the characters ELF, which looks like 45, 4C, and 46. And then you've got an ELF file, and that's followed by versioning information. So it makes sure that it has the proper version of the ELF libraries to run it. As an aside, if you ever were curious about how the interpreter directive works and you wanted to build your own code that did that, here's how it works. The text after the shebang specifies the interpreter. And if you want to see how that looks, you can do something like this. So here I've put user bin echo as my interpreter, and I gave it some arguments, and I put it in the file test. I made test executable, and I ran it. And what did it give me? It gave me 2 arguments. It took 1, 2, 3 as being a single thing, a single argument passed to it. And then it pasted on the name of the file on the end here. That's how the interpreter knows where to find the body of the file. And there you go. What if I wanted to split up? Well, you have to actually do work to do that. env has a switch -s, which will do that for you. And so then here it breaks it up into 1, 2, and 3, still tacks the thing on the end. So you can build your own stuff that runs as an interpreter in this way. It's pretty easy. And it can be very useful for a lot of things. All right, but you don't care about that. Let's get back to exec VE. So now you've got an ELF binary, and the file contents get mapped into memory using the segmentation information in the file. And where they go depends on a couple of things. There's a standard place to map stuff, map executables into memory, and we probably won't talk about why it's there this time, but we will talk about it when we talk about memory, I think. Okay, they don't just go into the address that's specified in the file, they go somewhere else. That somewhere else can be randomized if the address space layout randomization is enabled, which by default it is, and if the file is position independent, which it may be. Some header information gets collected. That's header information from the ELF file, and that gets placed on the stack in the auxiliary variables. That's then followed by the environment. Then the kernel puts the argument list on there in reverse order because it's on a stack. And then finally, it puts argc on the stack. And now the stack is set up. The kernel then goes and looks for the PT interp entry in the program headers. That's right, that's a segment table. Now the segment table the segments get loaded in memory. And so this thing gets loaded into memory so the kernel can go and look for it. The kernel's not going to paw around through your file after it's loaded. It's just going to try to find things in memory. So the kernel tries to locate a file. If there is one, if there is a PT interp, it specifies the dynamic linker to use. And you could write your own. That's a thing you could do. There are actually dynamic linkers that are used for debugging purposes. There are some much very simplified ones that are used for performance on certain systems. If you go out and look around for alternative dynamic linkers, you'll find some out there on the web. So the kernel tries to find the file that you specified, and then it maps it into the program's memory space. Remember, it's probably already loaded it. Something else has probably run that required it, and so it's already loaded it off the disk, and so the kernel doesn't want to load it off the disk again. It goes and discovers that that file is already mapped into memory. And so what it does is it just manipulates things in your table, your page table, so that it shows up in your memory space. Just maps it in there using mmap, which we will talk about when we get to memory. If the kernel can't find the file specified, it generates a file not found error and doesn't tell you anything else. It just you see a program, you run that program, and it tells you file not found, and you're like, what? The file's right here. It's because the interpreter can't be found. The program interpreter is nearly always relocatable. There are weird edge cases where there's an interpreter that's not, but that's so weird that it's barely worth mentioning. How do you know it's relocatable? You can look for the E-type in the ELF header, the E-type entry. And if you look at that and it's set to etdin, then you know that the type is a dynamic program, and that's how the kernel knows it. Kernel loads the program interpreter, and it will then set the thread's resume address to the entry point. Remember, I'm running in the kernel, and your program is over in user space. And in order to actually transfer control to your program, I have to do a context switch from kernel space to user space. And so what I do is I basically say the thread should resume at the entry point of the program interpreter. And then I do a context switch. Basically, I do an RTI, which takes me from the kernel space, ring 0, into the user space, which is ring 3. Hooray. Now the program interpreter is running. And what does it do? Well, it processes dynamic relocations. So it looks at scans through your file. It looks at the dynamic relocation table, which gets loaded into memory. And it tries to figure out if it can resolve all the relocations. And if it can't, it gives you an error about not being able to find a dynamic link library and exits. But if it can find all of those, then it tries to determine how to address that. And that depends on full, partial, or no railroad. And so once it's done the work that it thinks it needs to do initially, it goes and gets your entry point from the auxiliary vector table, and it jumps to the entry point. If you look in if you walk through it with the debugger, you'll eventually find a place where it's loaded your program's entry point into a register by walking through the auxiliary vectors, and then it jumps to the contents of that register, which takes it into your program. It doesn't call your program, doesn't treat your program as a subroutine, it just transfers control using jump to your program. It's a lot, but that's what happens. If the kernel doesn't find that you want a dynamic linked program. It doesn't find PT interrupt in the program headers, and it assumes that you're just a static thing that wants to run. And so it sets the thread's resume address to the entry point of your program, and it just goes. It just starts your thread, and you begin running at _start for your program. That's it. Entry point specified in the ELF header, it's usually called _start, but it can be renamed. And on most things on your system, you won't find it because the file will have been stripped. So how do you find the entry point? Well, you look at the ELF header. The ELF header specifies an address. Once you know where the program has been loaded, what that offset is, you just add that address to the program offset. That's the address at which your program is going to start. Your process must self-terminate. And the way it does that is it invokes exit, which is number 60. That's what we've been doing. If you walk through a lot of the programs on your system, you'll find that they call exit group, which is a system called 231. And that tells it to terminate all the threads in the thread group of the process. We've been living in a single threaded world. I'm not going to cover creating multiple threads in assembly language in this class because I'm sort of baffled as to why I would. It might be worthwhile for you to look at multi-threaded code and think about that a little bit, because it's a multi-threaded world, right? The world is parallel, but we have too much to cover to really give a chance to do that any justice. So most stuff is going to do exit group, and you'll be able to find that if you paw through the code. A process can also be terminated by the kernel, right? If the kernel doesn't want you running, you're not going to run. And the most obvious way is I send the process a signal like sigkill. And when I do that, when I send the process most signals, they can go to a signal handler inside the process. The kernel will pass that signal along to it, like sigterm or so on. But for sigkill, the kernel grabs that and says, you know what? I am going to go ahead and kill this process. And the way that a process gets terminated is the kernel removes its entry from the scheduler. So it just isn't going to run no more. And then it unmaps the memory. It deletes all the memory mapping for the program, and it's just gone. That's it. Like it was never there. So that's how your process starts up at start. That's how it ends. It ends with exit. Pretty simple stuff. Here's the basic structure for a process in Linux in assembly. Right, so up at the top here, I'm assembling, and then I am building a dynamically linked position independent executable. I want to have an _start, so I declare that. That's what the linker is going to look for by default. If I wanted something else, there's a switch for that. I think it's -E, and I can change the name, but really, why would you do that? Don't do that. Here's my _start, and when I arrive here, my arguments are on the stack, and the stack is aligned on a 16-byte boundary. Now, doing that is a bit tricky. Remember, the thing at the top of the stack is going to be argc followed by argv. So the system, in order for me to arrive with stuff on a 16-byte boundary, has to figure out how to put the stuff on the stack so that all its inputs supposed to be, and I wind up aligned. And it does some work to do that. That's not a trivial thing to do. I then get argc if I want by just going and grabbing the stuff that's the 8 bytes that are pointed to by RSP. I get argv by going and grabbing the address of the 8 bytes below argc. So notice that this is a move, but this is a load effective address, right? argv is a pointer to a pointer, and this is where I find the first pointer to a char, right? The first, what we would think of as a string, right? A string is a char star. And see, this is where I find the first character pointer. It's at this address. And so this gives me the address of this pointer, which is the pointer to the pointer, which is what argv is. All right. Then I can terminate the calling process. Exit was value 21, so I put 21 in RDI, which is by the calling convention. And remember, there's a slightly different calling convention for system calls than there is for regular calls. They differ in that, what is it? That RCX is used for, I think, for normal calls, and R9 is used for system calls. I think that's right. And so slight difference in what's done here, but first argument's an RDI, second one's an RSI, third's an RDX. Pretty simple stuff. So I put this as the first argument. Exit only takes one argument. Exit's number 60. I put the number in RAX. I do a syscall, and I'm done. And I will never reach this halt. I better not. If I reach this halt, I will get a seg fault, right? Because this will cause a processor exception because I'm not privileged to use halt. And so I'll get a seg fault, which is the universal way of Linux telling me something broke. There you go. What if I'm thinking about the world as a C program? Well, that's a little different. It's a little bit different in that my view is not going to be from somewhere inside the process as opposed to the process itself. So basically, C programs aren't any different. They're a Linux process. They have to have an entry point, which is usually _start, and they main in program interpreter, and they terminate by calling exit or exit group. They work the same way as everything we just saw. All the stuff we just talked about is true. It's just that some of that stuff is now provided for you. So the stuff that's provided for you is done because that tends to be platform specific, right? And the C language tries to hide that. So it looks to you like, oh, there's a main function and it takes these things and it returns an int, and that's how it works. And how those things get marshaled and moved around and passed, that piece of it is needed to communicate with the operating system, and in a way also to communicate with the processor. But all that stuff can be hidden from you. So that's what's going on here. It's still a process. It still does the same stuff. It's just that some of that information is provided for you to hide those details from you. The way that's done is we give you a few object files. The most notable one is crt1.o. It was not always called crt1.o. It used to be called crt0.o. And you'll still run across that sometimes on some platforms. That's the very primitive, super simple version that doesn't call constructors. And yes, there are constructors in the C runtime. Don't worry about that. It's not that important. crt1.o is the usual one. You may find, if you do a locate for CRT 1.0, you may find a few others on the system. And again, they're just different wrappers for your program. The most notable one is this one, GCRT 1.0, which if you build your program, your C program, with profiling turned on, you get that one instead, because it wants to enable profiling for your program. All right. So we've looked at this before. There's _start, which you have to have, remember? And this call followed by a halt, right? This halt is a little piece of visual information indicating that this call is never going to return. And if it does, we'll get a seg fault, right? Something goes really wrong with the stack and you wind up returning from this call, you will hit this halt and get a seg fault. So we don't want that to happen. This calls libc start main and it does not return. Libc start main doesn't return because it's going to eventually call exit group. If you want to know more about libc start main, you can go and look at the code for it. It's part of the glibc library. You can go grab Linux is open source. Go grab the code for it. Here's the function prototype for it. It's a little hard to find because the function prototype is in the C file with the actual implementation. So there you go. But you'll go find it, and you can find the implementation of it and the arguments it takes and so on. It takes a couple. Its job is to set things up for your main function, and it sets things up in accordance with the calling convention on the particular platform. So if you're in a 32-bit world, it's going to do things differently than if you're in a 64-bit world. And if you're on the ARM processor, it's going to do things differently than if you're on the x86, right? It's trying to hide these details from you but in accordance with the platform's calling convention. What it's going to do is put argc in EDI, argv in RSI, and envp in RDX, and then it's going to call your main. It's not going to jump to it. It's going to call it as a subroutine. And when your main returns, and it needs to return back up to the C runtime, back to libc start main, it will perform finalization. And usually there's nothing that goes on in finalization, but sometimes there can be. And then it invokes exit group to terminate the program. And you can trace through all this with GDB if you're super curious about it. So that's what it does. So as a result of that, the structure of your code will look a little different. You'll write a main, and you'll expect the arguments to be in registers. So the arguments are in registers, and the stack is misaligned by 8 bytes. The stack for this guy aligned the stack and then called main. And when it called main, that resulted in the return address being pushed on the stack, which is 64 bits or 8 bytes. The stack is not aligned on a 16-byte boundary. It's off by 8. That's okay. If you push RBP, the stack is now aligned. Congrats. You are a callee, right? The caller is libc start main, and you are the callee. If you called printf, you'd be the caller, and printf would be the callee. So when you think about callee saved and caller saved registers, you have to think about the context in which you are operating. Are you the callee in that context, or are you the caller? And you can be both, right? If I call printf down in here, I'm both. And I have to think about preserving the registers of the thing that called me and preserving registers that printf might use because they're callee saved registers. Arguments are on the stack as per the AMD64 calling convention. There they are. We just talked about that. When we're done, we return control to the caller. And the return value isn't not in RDI, which was the first argument to exit. It's in RAX. Why? Because that's what the calling convention says. And remember, we are now a called function, so we're following the calling convention. In this case, we're going to return 14, so I put 14 in RAX. I'm going to restore the callee saved registers RSP and RBP, and then I'm going to return. I have to get the stack back the way it was, so the stack pointer is pointing at the return value from this function. Otherwise, who knows what will happen. It's madness. Notice how I build it, I assemble it, and now I'm going to use GCC to actually link it for me, because GCC is going to go ahead and find crt1.o and crti.o and crtn.o and put them in the right order around my .o and build the file for me. And we may talk about those at a later time. They can be fun to manipulate. Whew. Okay, hopefully that was somewhat helpful. That combined with the little video, hopefully that will get things sorted out for you and make it make a little more sense. Let's go back to discovery and control flow. When we left off, we were about to talk about basic blocks, and we just ran out of time. So let's talk about basic blocks. Basic block is not a super complicated concept. It's just a linear code sequence. And the things that you need to know is there are no branches in except at the entry, and there are no branches out except at the exit. And that says single exit, but really you can end up in multiple places at the end of a basic block. And that's okay. Basic blocks are going to be the nodes in your control flow graph. And it sounds almost like they're proper programs because of single entry and a single point of exit, but they're not really. They're more akin to function and predicate nodes, because the last thing in your basic block might be a conditional branch, and that takes you to 2 different places. So it's like a multiple exit. So it's not really a proper program. It's really more like a single node. But that's good. That means that instead of having to deal with single instructions, I can now deal with big chunks, possibly huge chunks of my program, and treat them as single nodes. And that can really speed things up for my analysis. Basic block ends when the linear control flow ends. So when would that happen? Well, that would happen if there's a conditional branch. A jump, right? A jump takes me to a new address that's not the next linear one. And so even if I jump to the next address, I'm going to be very syntax driven and say, oh, that's the end of the basic block because I hit a jump, no matter where it takes me. A return or an I returns are how you return from interrupt handlers. Don't worry about it too much. Or a halt, right? If there's a halt, that certainly stops linear control flow, right? Because either it's going to halt the processor, that's going to stop things, or it's going to segfault, and that's going to stop things. One of those two. A basic block also ends when I encounter the start of another basic block. Why is that? Well, because I said no branches in except at the entry, right? Single entry. If I'm walking through and I encounter the start of another basic block, that means somebody is jumping in right there. Well, I better end before that. And so I end prior to that. So basic blocks are super common. If you look at code in just about any reverse engineering tool, it's going to break your program down into basic blocks because, again, they're just the nodes in your program's control flow graph, and they're super useful. So how do you find basic blocks? There's a simple algorithm to do it. In pass one, you identify what are called basic block leaders, the first address of a instruction in your basic block. And a thing could be a leader because it's the first instruction, right? The first instruction at the entry point of your program, clearly a basic block leader because that's where you go. So that's just your given address. And so there you go. We're going to just say that is a leader. It might be the target of a conditional branch, or it might be the address immediately after a conditional branch, right? Both of those are places where the linear control flow broke and where a new basic block starts. So if I say jump if equal to address 140, well, 140 is now a basic block leader because that's where linear control flow is going to start. And the address after that jump is a leader because that's a place where control flow might start. It could be the target of a call, or it could be the target of an unconditional branch, like a jump. So all those are places where linear control flow picks up and starts a new basic block. In part two, I have my list of leaders, and I walk through and I just collect the instructions that go in the basic block. And I just collect the sequence of instructions until I hit the next basic block, or I hit a terminator, something that stops it. And we'll see what those look like in just a minute. Some algorithms don't do this. They just blindly assume that they'll keep running until they hit another basic block or the end of your code. That's nice because that can mean that every instruction ends up in a basic block, but it can also be really messy because programs put a lot of no-ops in stuff, and that can be problematic. We'll see that in a moment. What terminates a basic block? An unconditional branch, like a jump. Halt, return from interrupt, conditional branches, looping constructs. Those all terminate it. Call doesn't terminate a basic block if it's going to return, right? So I'm going to call something, it's going to come back. Linear, from the point of view of my code, that's linear. That's I do a call, and then the next instruction happens. Right? The linear control flow continues. Same for syscall. If I'm doing a syscall to exit, well, clearly that's not going to return, and that's okay. I'm going to catch that because I'm going to follow that with a halt. All right. So here's some code. I honestly can't remember where this comes from. This comes from something in Linux somewhere. I forget where. I just grabbed it. It's code I've been using for a while. So here's a call, a move, a call, a move, a call, a move, load effective address, compare, jump if equal, pop, jump, no op, pop, ret, no op, compare, push, jump if equal, and exclusive, or to zero out EBX. There you go. Should be all stuff that you recognize. It looks pretty familiar to you. No unfamiliar instructions or weird instruction prefixes in here. Let's run the basic block algorithm. So the way we do that is fast one, we just look for leaders. And the first instruction is a leader. Great. So 6fox27 becomes a basic block leader just because it's the first instruction. Congratulations to it. It calls 46D0. So 46D0 is also a potential basic block leader because it's a target of a call. Boom, we have two right now. 6F27 and 46D0. Let's go to the next instruction. It's a move. We learn nothing much from that. But the next instruction is a call. It calls 46D0. We've already got 46D0 in our list, so fine. It's twice as leaderly now as it was before. The next one's a move, and then a call to 6fox70, which you see is down here below. And so since we're calling it, it's a basic block leader. We put it in the list. And so there it is in the list. Now we have three potential basic block leaders. The move doesn't add much for us. The LEA doesn't add much to it. Compare. And then we hit a jump if equal. This jump if equal goes to 6fox60, which is right here. And if we don't take it, we wind up here at 6fox51. And so both of these are basic block leaders. And so we'll add both to the list. So now we have this because it's a target of a branch, this because it is the first instruction after a conditional branch. Let's keep going. Pop, and then a jump. The target of that jump is already on the list, I think. 4C, nope, it's not. This is an error. I should have added this to the list. Who knows how long this has been in here? I think I just look at it and it looks so much like 46D0 that I don't see it, but that's wrong. So it should be on there. No up tells me nothing. Pop RBX tells me nothing. Return tells me nothing. No up, compare, push, jump if equal. Aha, now 6fox9D needs to go on the list, and the instruction right after it, 6fox7B, needs to go on the list. And so I add both of those. Here is my list of potential basic block leaders. One of these is out of scope. 46D0 is out of scope. It's not in the piece of code I'm analyzing, so I don't care about it. If I wanted to be thorough, I have to analyze all the code. And the reason is somewhere, some person might have added a line that says call 6F3E. And if they do, then this becomes a basic block leader. And I don't see that in this scope. And this brings up the reason why structuring is a good thing, right? If someone out there is referring to 6F3E and jumping into here, that is a reference that I'm not aware of. So this is not referentially transparent because somebody else can jump in here, and that can break my analysis. All right. If somebody's trying to build a ROP gadget, they might want to come in and use something like this pop RBX return in order to pop RBX and manipulate. This is a particularly good one because if I call this, it pops with the return address off the stack and returns to the parent. So I can do all kinds of mischief with this. So we need to know that kind of information. And to get that, you have to do what's known as whole program analysis, which is hard, but it's what you've got to do to be able to analyze it. And so turning a unwieldy program into a collection of structures means that now I can analyze those individual structures and not have to worry about that kind of craziness. Now, it's not perfect, of course, right? I can hide a conditional jump using computations and rely on Rice's theorem to show that that is in general undecidable. But, probably not, because I'm a human being and I want my code to work. Okay, so there we go. Basic block leaders. At the end, there's an XOR. We don't care about it. Boom, we're done. So now for each basic block leader that we found that's in scope, and those are the ones indicated by the little red arrows, we want to walk forward and collect the entire basic block. We're going to walk forward till we hit a branch, a turn, looping, or another block leader. The main one being another block leader. So we do that. we wind up with this. So this basic block contains all this stuff until I hit this conditional jump. Or another way to think of it is I hit this basic block leader right here, and this is where the basic block ends. So the basic block contains this call, move, call, move, call, move, this LEA, this compare, and this jump if equal, and that's it. That's all that's in this block. So control comes in here, and then control flows out either to 6Fox60 down here, or to right here. So it's you could imagine this being in a graph. This would be one node, and it would point to this node and also to this node. All right. The next one is pretty simple. I got a pop followed by a jump. So that jump takes me somewhere, and I would have these two instructions in my basic blocks, and I don't want that no-op. That no-op exists to pad out the space so that this is aligned on an 8-byte boundary, or in this case, a 16-byte boundary. And I don't care about this. And some tools would show me this as a basic block. And that's not useful because control doesn't exit here. Control exited up here. So to follow the correct definition of basic block, you would end it here. Another basic block, pop, and then return ends that one. I don't care about this stuff. And because when the leader was here, I ended it with this. And so these didn't get added to any basic block. Compare, push, jump if equal, that terminates that one. And this one terminates because I run off the end of my piece of code that I'm analyzing. This just contains a single instruction. So here we go. I wind up with 1, 2, 3, 4, 5 basic blocks for the piece of code that I analyzed. And they form a pretty simple control flow graph, right? This one, like I said, points to this one and this one. This one points out of scope. This one points out of scope. So I have two different exits from my little control flow graph. Sometimes that happens. That means I just don't have enough information. This one points to 6Fox9D, which is out of scope. Oh, I have a third exit out of it. And this one, points to whatever's after it, which I don't know what that is. So yet another jump out of scope. So there you go. I would want to analyze much more of the program to get a more reasonable control flow graph. Now, once I've built my control flow graph out of basic blocks, I can turn around and structure that control flow graph. And now I have something that's much easier to analyze. I can have a piece of assembly that has whiles and if then else's and stuff like that in it. And if I'm writing tools to try to analyze that, or like I'm writing tools for Ghidra to try to build structured code out of it, try to reverse it to C code, that's what I'm going to do because it's going to be helpful to do that. I hope this made sense. Why are we doing this? Simplifies analysis, right? All of these are some basic tools to try to simplify the analysis that I'm going to be doing later on. I get to figure out what this block is doing without having to think about what these other blocks are doing in the ideal case. You can be wrong about a basic block, right? There might be a jump table somewhere you haven't thought of. And so I might do something, so I can find a good instruction over here. I might move something in here from a jump table, and I could potentially jump, I could say jump to RDI here, and that would take me somewhere in the program. And so I'd have to do a much deeper analysis to figure out what that might be. I have to go look at the jump table, figure out what's in it, and try to understand it. What's in that jump table could be relocations. And so that's important that I understand relocations so I can figure out where the code is going. Okay, hopefully things are beginning to pull together for you. All right. So at this point, here's what I think we've accomplished. I don't think you can really do a good job of understanding assembly unless you've actually had to write some assembly. So you've written some assembly. It's a surprisingly complicated world of x86 assembly, and there's plenty more to learn. And we'll introduce some more stuff as we go along in the class. But by this point, you should know enough of the basics that you can go and look up stuff that you need to know. So if you're analyzing a program and you see a prefix like lock on an instruction, you can look that up. If you see a prefix like no trace, you can look that up. And if you see a weird instruction, you can look it up. So you should be able to do some, at this point, you should be ready to look at and analyze some programs. Now, just opening them up in a disassembler and staring at it is hard. You make tons of notes. You spend a lot of time figuring out that, oh, this is doing a very basic thing. It's just the compiler did something weird, or somebody tried to obscure it, or I was, not seeing it for a few moments. But there are lots of techniques that can help you, right? So we're going to spend the rest of this class talking about these specific techniques that you can use to automate analysis and do stuff with it. And there's a collection of basic program analysis techniques of program flow analysis, control flow analysis, like structuring and basic blocks, but also data flow analysis, like using live variables that can really help you understand what's going on in the program, can help you simplify a program, and can help you target answering a specific question about a program. Okay. So we've gotten through that first, hump, which is teaching you assembly. And you probably know more than you think you do about assembly at this point, which is I guess good. So live and dead variables, pretty extreme. And like real life, it's going to be really hard to tell what's live and dead. A variable is live, and we use this with respect to a particular point in a program's execution. It's live if and only if its value at that point is used in the future. Otherwise, it's dead. And this means that to figure out if a variable is live, you have to know the future. You have to know how it's going to be used later on. And if you're in a twisted spaghetti code knot, it's going to be really hard to figure that out. This is where structuring and basic flow analysis pay off, right? Flow analysis enables us to then be able to do live variable analysis. This kind of analysis is used all over the place. The compiler uses it. The compiler uses it to do register allocation. And we'll actually, I think, talk about register coloring later on, but you can do register allocation using this. If a variable is live, it needs to be stored somewhere, right? Because its value is important in the future. You got to keep track of it. If it's dead, it don't got to be stored nowhere because its value isn't important in the future. And so we don't care about it. Okay. And if I have a variable that's live here, and then another variable is live here, and they're never live at the same time, I can use the same storage for those two, save some space. Of course, everything is more complicated than you think it is because computers are always more complicated than you think they are, right? They're basically just machines for creating problems. So really, there are two kinds of liveness that people like to talk about. A variable is semantically live at some point in the execution of a program if, when I change its value at that point, it changes something that's externally visible in the program later. Subtle thing, but imagine this variable living somewhere in the program. The program's running, I halt the program, or I freeze it. If I change the value of that variable, it will change the future evolution of the program. Something about it will change in a way that's predictable. Okay. In that case, that variable is semantically live because its value is important to the behavior of the program in the future. It may be more or less sensitive to it, right? It might be that it only changes the evolution of the program if the value is 0 or non-zero, in which case I could change its value all over the place and not make a change. But if I hit 0, then it changes. So it can be a little subtle. It's like most things in computers, it's not nice and continuous. It can be very discrete. You don't have to step functions with it. But basically, if I change the value of it, something in the future evolution of the program is different. A variable is syntactically live at some point in the program's execution. If there's a path from that point to the exit of the flow graph where the value of the variable is read or used in some other way. Think about that. I can get that just by looking at the code. I look at the code and I see, oh, here's a variable, and oh, look, it's read here, or it's added to another variable here. So its value gets used. Oh, I'm done. That's syntactically live because it got used. All right. And as you can guess, the first one, semantically live, is incredibly useful, super helpful, and exactly what we want, and also undecidable. And the second one is problematic, but decidable. And what we would like is to be able to say that a variable is semantically live only if it is also syntactically live. So if I do my analysis to look for syntactically live variables, I'm going to get some that are actually semantically dead, but I'll get all the ones that are semantically live, and that's good enough. That may be good enough for me, right? Syntactic liveness is decidable. I can look at the program and go, oh, look right there, it's being used right there. In reality, it's always more subtle than you think, right? Because we live in a world in which there are pointers. And there may be pointers moving around pointing to the contents of my variable. At any given point, I freeze the program and I got a variable. I got a value on the stack. I say that's variable V. But at the same time, I've also loaded that value into a register. And I may have another pointer somewhere else pointing to that place on the stack. And so the variable can be modified in ways that are non-obvious. To figure that out, I would need to solve the points to problem, figure out what pointers point to. We will cover that later. That's going to be a thing. But just sort of be aware that, like with everything we talk about, any nice, clean mathematical model we build of the world is immediately screwed up by adding a computer to it. Just the way the world works. All right, so we're going to use syntactic liveness to try to approximate semantic liveness because that's what we're trying to get. What does that look like? Here's some code. So not super complicated code. I've got a little function called work, takes a single argument C. I declare some local variables A and B. I set A equal to 0. I do a loop here while A is greater than 9, not initially. So what's going to happen here? Well, I come in and do some stuff with the variables, and then I return C. Okay. Without knowing anything else about it, I want to just apply a dumb algorithm and get through my day. Well, let's see if we can figure out what's going on here. So if we take a look at line 9, we see that C's value is being used. It's the return value for the whole thing. So C must be live prior to this line. So when we talk about liveness, we're going to talk about not what's live or dead at a particular line of code or a particular instruction, but what is live prior to and after an instruction or a line of code. So immediately prior to this, C is live because its value is about to be used. A and B, right here prior to this line, are dead. They're dead because they're about to go out of scope, right? Nothing uses their value. And here I return, and the stack gets cleaned up, and I'm done. So C is live, but nothing else is live right here. if we go up to line 7, A gets B times 2. We notice that the value of A is being overwritten. So anything that was previously stored in A is now lost. What does that mean? That means that immediately prior to this line, A is dead. We know it's dead because any value that A had could not contribute to the program's evolution because it's going to be erased right here. The very next thing we're going to do is erase it. A is not used here in this line, so A is still dead. A is used up here to give a value for B, so A is live right here. Now, what if B were actually never used and we determined that B was dead here? Well, again, that's one of the cases we have to decide what we're going to do. Is A dead because it's only used to contribute to a value that's going to be dead? Okay, we'll have to think about that. But that gets the basics for it, okay? We're going to work backwards to the program, right? You want to know what happens in the future? Well, the future is down here at the bottom, and the past is up here at the top. So we're going to work backward in time by going backwards to the program to do liveness analysis. And that's fairly common, okay? There's a lot of analysis techniques that require you know something about the future, and the best way to know about the future is to walk backwards through a program's flow, okay? So at line 7, we have A gets B times 2. And we can think of the analysis we want to do for this like it says here. L values, right? So in this case, for this instruction right here, A is an L value. It's a value that gets written. And B is an R value, right? It's a value that gets read. So L values can be removed from the live set because we're overriding them. And R values get added to the live set because we're using them. And by live set, I mean the live set prior to this line. So if down here, A was live, when I walk back through this line, I remove A because it's an L value, and I add B because it's an R value. And so if A is live here, up here, A is not live, but B is. Does that make sense? And we work our way back up. So we know C is live immediately prior to this return. We walk into the loop. We know A is live because we use it to control the loop. So A and C are live here. I walk back one, and now B and C are live here, right? Because I discarded A because it's an L value. I added B because it's an R value. Nothing here mentions C, so C stays in the set. So just C, C and A, B and C. And I walk back one more. I remove C from the set because it's an L value. And so now just B is in the set. But then I add it back along with B. It's already in the set, so I add it. It's still in the set. But I add C as well. So here it's C and B, and up here it's still C and B. I discarded it, but then I added it back. So it's still in the set. A very primitive kind of analysis, but it will work pretty well for us. We can walk back one more line. Look at this one. So right here we have B and C live. This tells me discard B, so now it's just C. This tells me add A, so now it's A and C here at the top of the loop. A and C are live. At the bottom down here, it was just C. Moving in at the bottom of the loop, it's A and C. Up at the top of the loop, it's A and C. That's interesting. A and C, A and C. In the middle, it changes a little bit, but here it's A and C at the top and the bottom of the loop. That makes sense. We'd like the same things to be live at the bottom. They're live at the top. If they are, we're in good shape since it's a loop. If it wasn't the case, we would take the union of them because it's a loop. All right. We can keep walking back and that'd be fine. But here are the things we learned, right? Prior to line 5, it's A and C. Prior to line 6, it's B and C. And prior to line 7, it's B and C. Okay. I'm entered to the loop, only A and C are live. B is dead. Whatever value it held when we failed to initialize it up here, it held something. never gets read, so it doesn't affect the program. And that's good because it was some random value in memory. We don't want it to affect the program. Okay. We can also think of this as what is live or dead on an edge in the flow. So if I built a flow graph for this, or I built a flow graph, let's say, out of basic blocks connected, I could define what's live on the edges between nodes of my graph, and that could be really useful, right? If I've got a complex piece of code and coming into it, I see that only like one thing is live, then, and there's a whole bunch of stuff being done with stuff that's not live, I don't care about that. So there can be some really neat things that fall out of doing liveness analysis, and we tend to think of it in terms of what's live on the edges. So the edge between this node and this next node here, between these two, is what's live between 5 and 6. We look down here and we see that A is dead, B is live, and C is live. So we can give a live edge set for every variable. That's another way to do it. It looks like this. This tells me where each of the variables is live. And if we look at this and sort of squint for a moment, you might see something interesting. A is live on 3 to 5, 7 to 8, and 8 to 5. That's the return of the loop here. B is live on 5 and 6, and 6 and 7. C is live everywhere. These two sets, the set for A and the set for B, are disjoint. This tells me that A is never live when B is live, and B is never live when A is live, right? I only ever have one of these two. Since they're never live at the same time, they could share the same storage. In fact, they could share a register or something like that. And if they could share the same storage, do we need both? And weirdly, it turns out you can discard one of them and it doesn't matter. So here I've thrown away B. You have to work to convince yourself of this, but this code is equivalent to this code. I figured out I don't need both of them. I just need A. So I've already simplified my code by reducing the number of variables in it. There you go. This, of course, makes an assumption. The assumption is that I know everything that happens to it. Nobody is long jumping into my program at this location and doing something, right? If they are, then I didn't know about that and my analysis could be wrong. But again, in a nice structured programming world, I get to make those assumptions, and that's very helpful. How does this help? Well, liveness can reduce the number of things I have to think about. Especially in assembly, it can lead me to being able to discard entire instructions, right? Let's say that I'm analyzing a piece of code and I want to know and it's going to jump to a location in RAX, and I want to know what's in RAX. And so what I would do, right? I mean, just think of what you would do to figure that out. You'd walk back through the code, look backward through the code, trying to find places where RAX was manipulated. And you're like, oh, it's being set to what's in RBX here. So now I got to work backward and figure out what's in RBX, right? You would do that kind of live analysis sort of intuitively. And a lot of the instructions wouldn't matter to you because they don't involve RAX or RBX or anything that's involved in computing what's in RAX at the end. And so you could throw those instructions away. And the result would be hopefully a much smaller set of instructions that you could directly analyze to find out what's in that register. Okay. This is a fundamental technique in data flow analysis. And we're going to mention live variables in almost everything we talk about from here forward, right? They're going to show up everywhere because it's a really foundational piece of data flow analysis. Whew. All right, so before we get to talking about the new homework, because it's Wednesday, are there questions on any of this? Hearing silence, I'll get to the homework. We're going to shift gears. It's not assembly programming this time. Isn't that great? Instead, It's Python. You're going to write some Python code. So I want you to write a program in Python. You can use the PyElf tools and the capstone. In fact, you'll need to use those too. Your program is going to take a single command line argument which specifies a file. And here's what you're going to do. You're going to open the file. You're going to find the text section, and you're going to disassemble and print out the disassembly of all the code in that section. And you'll name your file disassemble.py. Please name your file that. Please name your file that. Again, I'm trying to automatically check your code. And so just name your file that. I do some normalization of stuff that comes to me, and that's fine. But if you name your program something bizarre, I'm not necessarily going to recognize it right off the top. All right. Or at least my automated tool that checks it is not going to recognize it off the top. It tries to be pretty forgiving, but even it gets baffled sometimes. All right. So here's what your output should look like. So if I point my disassemble.py at ls, or at the Python executable, or at any old thing on the system, it should be able to go and find that elf file, and if it exists, and open it up and just start dumping stuff out. And you'll notice I've got an address in front of each one of these. So you need the address, and then you need the mnemonic and the operands. And if you go back and look at where I introduced Capstone and PyElf tools, I actually think I ended up showing you most of the tools that you need to make this work. Now, since this is a program that you'll want to be reliable and you're going to build on, you'll want to watch for stuff like file not found, or maybe you give it a directory, it's going to give you back an is a directory error when you try to open it. So these are exceptions that can come back from open. For elf file, you might get an elf error, which says, I can't parse this. Okay, and you might want to, if you don't want to, it can be hard in Python. It's not like Java. It can be hard to figure out what throws an exception and what exceptions are thrown. You only find that out sort of experimentally, which is a weakness in Python, admittedly. And so you can't always be sure you're catching all these. What you can do is look to see if the thing that comes back is none. Maybe it didn't throw an exception. Maybe it just didn't do anything. And so you can check it for none. And the way you check for none is you can check for equal none. That will work. That's not the proper Pythonic way to do it. The proper Pythonic way is to say is none. So, but you can find that out. If you write equal none and you run pylint, it will then tell you you should change it to this. Pylint is your friend. You'll want to debug, and you'll want to write errors. And I've given you a small piece of code in debug.py. It's attached to the assignment in iLearn. It's some Python code that you can import. You can just say from debug, put it in the same directory as your code, import, and you can import these three things that it provides. Error writes an error message. They look like this. They show up red, bolded, and in whatever the appropriate color is for your terminal. And so there we go. You can write debug messages. So they look like this. You turn them on by saying capital debug, equal debug. You can give it a list, a comma separated list of things. They all show up in a variable in the program at runtime called debug in all caps. It's an array. And you can check to see if something you care about is in this. So you might want to have something that checks to see if Fred is in debug. And if it is, you just print Fred. So down here where I said Fred is in there, it will print Fred. Up here, I didn't turn debugging on. I just passed it Fred and it said Fred. So simple, simple, simple stuff. Hopefully pretty straightforward. Here's a little piece of code that shows the use of it. Some hints. You might want to just work through the disassembly at the IPython prompt because you have some pretty handy tools. You have tab completion, you can do help on things, and you can sort of figure out what's where as you walk through it. You want to check for and handle error cases. You can format that number I showed you right here to that. That I created using an F string. So you put a little F in front of it. I put the 0x prefix, and then here's address, which could be a variable name, colon 016x. It says pad with zeros to 16 places and write in hex. So it looks a lot like a C format string, except with a curly bracket and then a colon at the end. And so you get 0x 16 hexadecimal digits and then a whole colon. Some things you might want to consider importing, right? Where do I get started? What do I need? You're going to need ELF file that comes out of the ELF tools. Here's the path to it. If you want ELF error, it's not in here. It's in a different part of the ELF tools tree. It's in common exceptions. From Capstone, you're going to want CS. That's the thing that builds disassemblers for you. You'll want that because you're on the x86 architecture, and you want that because you're in 64-bit mode. How do those work together? That was covered in the previous lecture. And if you may want debug and error, you might not want capital debug. It's up to you as to what you want to do. I'm going to run, when I run your program to check it, I will run it without any debugging turned on. So you can debug to your heart's content. And if you want special output on stuff, you can use capital debug to enable it. And I will not check that. That will not be something that I will care about. Use pylint. Strongly advise you to use pylint. You don't have to have types on things and use MyPy. It might help if you did. It might be that it takes you too long to write the code because you spend all your time looking at how do I encode a type hint. If you don't want to do that, don't do it. But definitely use pylint. Pylint's going to catch things and help you out. Next time, we're going to talk about two more techniques: trace tables and single static assignment. And those two really work together to help you figure out the end result of a computation. All right, that takes us to the end. Are there questions?